Good morning and good afternoon, everyone. My name is Khushi Jain, and currently I'm in third year studying at Daulatram College, Delhi University. It is my honor to welcome you all to this session at TEAS 2025 Networking International Conference on Emerging Trends in Expert Application and Security, a truly global academic initiative hosted by WSG University, Poland, and managed by KK Consultancy. The conference proudly reflects the spirit of global academic integration, strengthened by the presence of esteemed partners, JECRC University, Jaipur, IES University, Bhopal, and the community support of Shri Karni College, Jaipur. Our publication partner, Springer Nature, brings scholarly rigor to this initiative through its Scopus-indexed and highly reputed LNNS services. This year, we received an overwhelming response from across the globe with over 500 paper presentations after eliminating AI-generated and plagiarized content and following a rigorous peer review process led by an expert panel of academicians and industry professionals. Only the top 90 players were selected for the presentation. Following their successful presentation and based on recommendation from our esteemed session chairs, the paper will now be published by Springer Nature. With that, I am pleased to introduce our session chairs, Ms. Cecilia Ma'am, a professor at AI Lab, National Technological Institute of Mexico, Mismatla Campus, Mexico. I request Ma'am to please address the session.
Thank you so much, Professor. Good morning and afternoon, everyone. Welcome to this technical session.
Good morning.
Thank you so much, Dr. Jay, for the invitation.
Thank you, ma'am. Before we proceed further, I would like to share some important instructions for all the paper presenter to ensure smooth and timely session. First, each presenter has 4 to 5 minutes. Please stay within the time limit. Second, briefly cover your research, context, objectives, methodology, key findings, and conclusion. Third, a short question and answer may follow your talk of 1 to 2 minutes. Keep response brief and forward. Last, keep your mic muted while you are not speaking. Stay for the full session and support the fellow presenter. With the permission of our session chairs, I would like to proceed our paper presentation and to invite our first presenter of the day with the paper title Innovative Method for Contact Identification of Fragments in a Patient Body Based on Machine Learning, presented by the author with them oral. I would like them to over the stage. Okay, so we'll proceed next paper presentation. That is the paper titled Development of AI CR Clustering Algorithm for NOMA CR System. Paper ID 458 by Samita Samir Tikra ma'am. I would request the ma'am to please take over.
Okay, thank you. Good morning and good afternoon. Is it audible? Hello.
Yes, ma'am, it is audible.
Okay, now I am going to share my paper first. Is it visible? Hello.
Ma'am, no, it's not visible right now.
I have shared the screen.
Yes, ma'am, it's visible.
Yes, ma'am.
Okay, thank you. Good morning and good afternoon all. Myself is Smita from the Department of presenting the paper on development of ANCR clustering algorithm for TEAS system. Today I will present this paper or discuss this paper based on these contents. Basically, the major challenges for the major challenge is the explosive growth of wireless devices has led to spectrum scarcity and urging the need of efficient and intelligent spectrum allocation. As the number of resources increases, that's what the scarcity problem increases. The major challenge in this is diversification of the demands, fair power allocation, and dynamic and real spectrum allocation. In this case, these are the major challenges, and these are overcome by the CR and the NOMA technique. CR is enable the dynamic spectrum access by allowing the secondary users which opportunities to utilize the unlicensed spectrum have emerged as a promising solution to address the spectrum scarcity. Whereas NOMA recognized as a key enabler for 5G and beyond wireless network due to its ability to support multiple users on the same frequency channel and power domain multiplexing. Now,
Yes, ma'am.
taking on the third based on this, they are trying to overcome these challenges. So, in first and second, they are using some agglomerative clustering for the data clustering, urban planning, and for assembling the similarity. In second paper, they are using the technology. They have not been implemented for multi-scale of dynamic spectrum allocations. Now, in short, the abstract of this paper is like that. In this paper, the machine learning with CR NOMA is used to enhance the spectrum efficiency dynamically. The new algorithm uses the combination of agglomerative clustering with CR NOMA is designed and used for 6 different clusters for the formation of different applications like background download, emergency services, voice call, and online gaming. In this case, first of all, the 100 episodes considered for the multi-user CRM design and development. After that, this multi-user CRM system is designed. Tagger data set is used for this algorithm was implemented using the Python IDE. For the performance evaluation of this developed algorithm, it is compared with other machine learning models that is based on RT-square, MSE, and RMSE. And last is spectrum propagation is done and the results are displayed. In this case, there are the number of users on the left side that try to access the services provided by the base station. Now, the ANCR algorithm will present the base station and by using formation of NOMA CR for and pairing, users will be formed and will be divided into different clusters based on their application. That is the objective of this major objective of this paper. Now, the multi-user CRS system is designed. Here, the 100 users are allocated based on their RSI value. For example, if you see the node number N20, it has the RSI value is 96.4 as compared to if you observe the node
Yes, ma'am, it is audible.
that is implemented with the design of our new ANCR algorithm. Here, the every user from 1 to n, that is the number of users per set of them. First of all, we calculate the users matrix, then we find out the distance matrix according to the linkage method. User pairing is formed, that is near and far away. Then we combine the clusters of I to J to form the new cluster K. We modify this according to each iteration, and then make sure that interference and time power domain limitations are added. Also, by using Scopus principle, less power is provided to the near and near user, and more power is provided to the far away users. Channel allocation is provided while maintaining the primary user's interference limitations. Internally optimize the resource allocation is done based on spectrum efficiency and equity. It will return the clusters and resource scheduling and power distribution. Now, if the user's matrix is opted, then if you observe that on the same of that is there are the first here the same 8 samples, number of samples of the users are shown according to the data is taken from the 100 users. Here the number of 5. We will find out that the users is maximum for these two. That's why here the priority is provided. There, that is the one, and that is provided if we observe that these emergency services have the highest users among these number of applications. That's why first priority is provided to the emergency services. Accordingly, the priorities are provided to the different applications. Now, based on that, these are the different applications that find out background download, emergency services, online gaming, streaming, video call, web browsing, and here the priorities are provided. Emergency services accordingly provided the first priority, video call second, and accordingly the priorities are provided, and the background download has the least priority, that is the 6th. And dendrogram is used for the formulation or reducing the is used to understand the relationship between the data points. Here the points that are closest together in distance are merged first and to emphasize their similarity. Accordingly, the clusters are divided into the 6 types. Here, the result of this commercial cluster formation is shown. Emergency services online gaming are all different clusters are shown by the different colors. Red is used for the online gaming. Now, the results of this KNCR algorithms are compared with machine learning algorithm based on MSE, R2 and RMSE value. Here, if we find out that these are the mathematical formulas which are used to find out the R2, MSE and RMSE. Based on that, compared with algorithm entity regression, gradient descent regression, esteemed regression, we find out that R2 value of ANCR algorithm is 0.9645, MSE is 0.0083, and RMSE value it has 0.0074. By observing all these values as compared to these different algorithms, we find out R2 value of ANCR is maximum, as MSE value is minimum as compared to all these algorithms, and also the RMSE value. Now, this is the visualization of that. If you find out here, the ANCR algorithm has highest R2 value and the less MSE and the RMSE value. For that indicate that ANCR algorithm is the base in that finding the predictive values of the data points, and it has the base scalar values. Now, this algorithm is used for the allocation of the spectrum. Here, the different clusters that are shown by the different colors, and spectrum is allocated using this ANCR algorithm. We find out that here observe that the pattern is not the same. It goes on the similar the increasing and similar decreasing. Here the ANCR strategy prioritizes the spectrum allocation based on their user conditions, user input conditions. For example, cluster 1 and 2 efficiently distribute the list of 5 Those are first in setting efficiently out of higher reputation, and this whether here the dynamic spectrum allocation is provided by this KSDR algorithm. Now, thus, the multimedia traffic and the connectivity. In short, the summary of this paper is like that. As the multimedia traffic and the connectivity have grown exponentially in mobile communication in the recent year. For 5G and the beyond network, dynamic spectrum allocation is the key requirement. Therefore, in this research or the paper, the new NCR algorithm is designed and developed first for maximizing the spectrum efficiency. After receiving the data from large number of users, base station computed its value, and for this purpose, a multi-user CRM system is created. The gather data set is used to develop the ANCR method, and which is implemented with the help of Python IDE, which separates these individuals into the various clusters. Based on WSG and Scopus, the average English method is find out, and the results are compared here. We find out that ANCR method is the good. These are the references, and thank you all. Any questions for the I'm stopping sharing.
Thank you so much, ma'am, for your insightful and well articulated presentation. We are open to questions now. If any, please. Okay, so if there are no further questions from the audience or the session chair, we shall proceed further with our next paper. I would like to invite our next paper presenter with the paper ID 313. With the paper title LiDAR to Brain Interface, a novel approach model for converting LiDAR data into neutral compatible electric signal for brain implants by author Chinmay sir. Sir, it's over to you. Yes, ma'am.
So, good afternoon, everyone. I am Shri Karni and I am a student in KK University, India. And of course, here are some students. We are going to present a paper on the topic reputed interface, an approach for neural compatible motion simulation. So let's start with the picture. Millions of people suffer from vision loss, and current solutions often require distant surgeries as they implants. Our question was, can we skip our altogether and send environmental data straight to the brain? So we chose LiDAR, which captures detailed 3D data and provides excellent depth in spatial awareness. Our aim here is simple. Take LiDAR's data and convert it into signals that the brain's visual cortex can understand. We reviewed existing approaches, and most of the cameras which we use to statistics give 3D images, and hence they lack limited depth information. On the other hand, there are models that incorporate supervised machine learning in neural encoding.
Sorry for the disturbance, but still the PPTs are not moving.
It's not moving?
Yeah.
I'm very sorry. Am I on the literature right now? Can you guys take a literature review?
No, ma'am.
No.
Am I sharing? Can you see my screen now?
Yes. Now it's
Yes.
So we reviewed existing approaches and we found out that most visual prosthetics used are camera-based, which means that they lack limited depth in image. So on the other hand, we saw that supervised machine learning was also an approach that was used for neural encoding, but it requires user data, which is often not found. Now, LiDAR's role, as we know so far is primarily in robotics and autonomous vehicles, but not in brain computer interfaces. So the clear gap that we are addressing is that current UCRs do not use them, and they aren't very biologically realistic. So the key problems that we noticed are that most solutions are invasive and they need implants that carry surgical risks. And devices don't give a true sense of depth or environment, and the real world is messy and nonsense. So our idea here is to combine rigor and neurosimulation in a non-invasive way, which means encoding activity data directly into brain compatible signals. Our methodology, our methodology says that we have like 4 steps that we have incorporated here. So the first step is that the LiDAR scans the environment and collects 3D point cloud data. We then convert this into 2D images, but keep the depth information intact. Then a CNN simulates how the brain's visual cortex would respond, and finally we generate signals that look like natural brain activity. So the goal here is to make artificial vision feel as real as possible. Now I'm going to explain the methodology in depth. The first step, which is data acquisition and reprocessing, it says, in that step, the LiDAR gives us 3D point data, which we then clean up and normalize for easier computation. We also filter out the noise, so we're working on with accurate data. In the second step, which is LiDAR to 2D image conversion, we project the 3D point clouds onto a 2D point. The depth is shown using grayscale or color maps, so we don't lose the sense of structure. And now this is crucial because it is helpful to generate meaningful neural simulation. In the third step, the CNN mimics the visual cortex by detecting edges, texture, and patterns. Now what's unique about this is that we do not really require to train it. It uses random bits, which mimics quantitative data code and produce biologically realistic calculations. In the fourth step, which is cortical signal generation, each output bit becomes a science-level bit in which the proper calculations can be developed. We add Gaussian noise to mimic the natural variability in the neurons, and this gives us dynamic signals because similar to the active brain waves. This is the pipeline of the purpose of methodology today. So, what we achieved was that we developed the depth of the LiDAR data, the CNN activation highlighted these structures, and the generated signals look like the patterns that you would see in a normal visual cortex. But we're not recognizing objects yet, just capturing structure and depth. So in conclusion, we built the first pipeline that converts LiDAR 3D data directly into brain compatible signals. So this opens up quite a lot of possibilities for the vision investigation domain and system tech. The next steps that we or the world can pursue are to add object detection and semantics to this model, improve real-time processing, combine LiDAR with other sensors, and explore low-power data hardware. Here are the references, and thank you all for listening.
Thank you so much, ma'am, for your insightful and well-articulated presentation. We are open to questions now, if any. Okay, so if there are no further questions from the audience or the session chair, we shall now proceed to our next paper. With this, I would like to invite our next paper presenter with the paper title Plant Leaf Disease Detection from Deep Learning Techniques, a review with a focus on transformers and explainable AI. I would request Ms. Harshita ma'am to please take over the stage.
Is it visible to all?
Yes, ma'am.
Is it visible?
Yes, ma'am, it is visible. Yes, ma'am, you are audible.
Okay, good. Okay, so I'll start my presentation. Please let me know if slides are moving or not. So, topic of my presentation is plant leaf disease detection with deep learning techniques. A review with a focus on transformers and explainable AI. During presentation, I tried to conclude all these points, which is introduction, problem overview, detection pipeline overview, machine learning architecture, CNN-based architecture, transformer-based models, about the explainable AI, review of literature, hybrid architecture, conclusion and future works. So my first slide, introduction. Agriculture plays a critical role in ensuring global food security and economic stability. However, plant leaf diseases, particularly those that affect leaf, can cause severe damage to crop productivity. Traditionally, diagnosis method often rely on manual inspection, which is time-consuming, inconsistent, and requires expert knowledge. In recent years, deep learning has emerged as a transformative technology to automate the process of disease detection, and CNNs were the initial drivers of this progress. But they have limitations such as high data requirement and lack of transparency. Now the field is shift towards more
Sorry, your slides are not advancing.
I'm still in the introduction one. If it's not moving, that's fine. Is it? Can you see the introduction slide?
The first slide.
No, it is the starting slide.
I mean, it's the very first slide.
Is it now visible? Introduction slide.
No.
Now visible? Is it now visible?
Ma'am, table
Yes,
of
ma'am.
content slide.
Okay.
Yes, ma'am. Yes, ma'am,
Okay.
introduction. Yes, ma'am.
Okay, perfect. So, okay. So in recent years, deep learning has emerged as a transformative technology in the process of disease detection. CNN were the initial driver of these progress, but they have limitations such as data requirement and a lack of transparency. Now the field is shift towards more advanced models like vision transformers, bird-inspired architecture, along with the explainable AI technique that make the prediction more interpretable and actionable for end users, especially for farmers. Detailed pipeline overview about how it works. So basically it divides into 5 processes. Every time according to advancement, it add a different layer, but the basic pipeline is data acquisition, data pre-processing, segmentation, feature extraction, and classification.
In data acquisition is a very important process for the better accuracy of the model because it depends on the quality of the data samples and uh, quality depend on the type of camera and its positioning. People capturing picture through digital high resolution cameras and Android camera for data pre-processing, and this is a distortion and noise removing process that makes the process easier. Generally, pre-processing techniques are cropping, image enhancement, conversion of color space, etc. The functionality of the process always differ because it also depends on the image quality. Then it comes to the data segmentation, because after data acquisition, pre-processing happened where we completed all the cropping, noise removal or other technique before the segmentation. In the data segmentation, this is the process of splitting the plant leaf images into different region or subdivision to emphasize and focus on diseased area. And in this step, step is important because it allows the model to distinguish between disease-free or disease like contaminated leaf area, and which improves the accuracy of the detecting diseases in the plant leaves and their classification. And after segmentation, it passes all the properties to the feature extraction. This process differentiates one specific image area from the rest, and this process always comes before the classification process and then examine the object, and after that assigns the class label precisely. It works around the color, texture, and shape for the better identification and recognition. And in this process is important because after whole feature extraction, the output of the feature extraction pass to the classification, and then classification process the plant leaf disease in immensely dependent because of the extracted part of the feature. And then classification happens where process identifies and recognizes the diseases in the plant leaf, and it starts by taking the images from a training set and that are employed to the train the classifier, and then this trained classifier recognizes the images from the test data. The objective of the classifier is to identify the unhealthy and healthy leaves. After the detailed process, we finally reviewed our techniques by machine learning, CNN-based transformer, and then explainable AI. So first, machine learning. Before the deep learning became popular, some traditional machine learning models were used for the plant leaf disease detection, and these approaches relied heavily on handicrafted features and structured pipeline. Notable models include SVM, BPMN plus PCO, sometimes PCO separately, and then GMM, K-mean, and MSSOR, which were effectively binary classifiers, BPMN and PSO for better convergence. GMM were used for a background subtraction and segmentation, while K-means clustering helped in isolating disease area. One of the more recent advanced method is MSSOR, which is Memetics self-swarm optimization algorithm, which combines the metahoustic heuristic optimization with texture and shape-based feature to improve the classification outcome. These models followed a pipeline of manual feature extraction, for example, through color histogram, texture description like GLCM, and shape indices, followed by the feeding those features into the classifier. While accurate on the clean data sets, and they struggled with the image noise, variable lighting, and complex patterns. The major drawback of machine learning was that they were need to extensive domain expertise to extract the feedback. If there is poor scalability across the plant species, limited adaptability data, then this led to the foundation of shift toward end-to-end deep learning model, because this was, if there is a noise or bad quality images, then it also hard on the output. Then CNN-based architecture, it is convolutional neural network, and have been foundation of architecture of image-based diseases. And throughout the multiple years, we received a lot of models for plant leaf disease. Several models have been widely used in this domain. For example, VGG16, ResNet 50, and these are the deep high-capacity network, mobile net, which is optimized in lightweight application for plant leaf disease detection, YOLO 5, and tomato leaf disease detector, which is like Tolle. These domains are very specific for the plant leaf disease. The strength of CNN, which was the ability to extract hierarchical features from the input, such as edges, shapes, color, without the need for the manual feature engineering. And this has to lead to high accuracy in many studies, especially when using the benchmark data set, for example, plant leaf disease or big data set from JECRC. But the limitations were motivated towards more robust and interpretable architecture, because for the accuracy, we need more data and large-scale label data set, which cause to overfitting and imbalance. So that's why we need to shift from CNN to transformer-based model. Transformer-based models are recently been adopted in the plant leaf disease detection domain, and making significant evaluation from the traditional CNN approach, which is VIT, Vision Transformer. And in the transformer, VIT is a baseline where the image is divided into patches during the feature extraction time, and that embedded and passed through the self-attention layer, and it captures the global pattern that the CNN typically miss. And then VIT introduced a self-supervised VIT style learning method adapted for vision tasks, and this reduced the dependency of large labeled dataset, which was one of the limitations in the CNN. And then came VT, which is a very lightweight transformer designed specifically for mobile and edge environment to detect plant leaf diseases. These models are integrated well with the explainable AI tool like Bright, Stem, and Line, offering the visual insight into the model decision and essential feature for the real-world agriculture adoption. Now we have explainable AI. So this is quite new for plant leaf disease detection domain. And why explainable AI? Because this is very crucial part for the model deployment in agriculture. Deep learning models like CNN and transformer, despite high accuracy, often lack transparency. They are black boxes, so you can't see the internal processing. We just feed something and we have the output. But this becomes a problem of domain like a plant health, where the users such as farmer must understand and trust the model. We have some common tools in explainable AI, which is GridCam, SAP, and Line. So GridCam is most commonly used in explainable AI because it produces the heat maps that overlay on the leaf image and indicating which are influenced by the model. And SAP technique tool is used a game theory approach to qualify the contribution of each pixel or feature for the prediction. About the Line works for creating a simpler local model around each prediction, which can be inspected more easily by the domain expert. And these will not only improve the user trust, but also help to researchers to define and debug their models. the basic process of using explainable AI for the plant disease detection is, if we begin with the input image, it is passed into a trained deep learning model like CNN or transformer. The model makes a prediction about the disease class such as early, blight, or healthy. However, instead of stopping there, we pass the model internal to explainable AI tools like GRAD, CAM, SAP, or LINE, and these tools are generate a visual explanation, typically a heat map that shows which part of the model focus on making the decision or prediction. And this makes the model decision transparent and trustworthy for end users such as farmers, regulators, and also for the developers, so that we can focus on which part is problematic or through which part we can access the output. So for this, I compared during the review of literature for ML, CNN, and transformer. And I also explained in my last slide like how machine learning, CNN, and transformer approaches and their features, data requirement, and scalability, and how they are lagging behind than the others. And these are my papers where I go through and explore their differences and understand their accuracy with the data sets, and which papers use explainable AI with their accuracy, and the paper which are not using explainable AI and their accuracies. After all these review of literature, try to propose a hybrid architecture using CNN, transformer, and explainable AI. In this hybrid architecture, as I explained in my last slide, that how explainable AI architecture works if we use for the plant leaf disease detection, that the leaf image first processed with the CNN backbone for feature extraction, because CNN are excellent for capturing the local feature such as small lesion or a diseased part or color variation in the small area, and then these features pass to the transformer head, which uses the self attention to make a global dependency across the entire image, which is helpful for the understanding the large area or the depressed area of the disease pattern. And after that, it's generating the prediction with the help of explainable AI tool, which is GRAD, CAM, or LINE. The tool with result, it also generates the heat map that explains the decision that why this output comes, and then it would be better for the developers and also the farmers or regulators who are looking or seeking for the prediction. Future work and conclusion. To summarize my presentation, so deep learning has significantly advanced the automation of plant leaf disease detection, moving from the manual inspection to fast and scalable systems. CNN brought a high accuracy but lack of transparency and struggled and generalization. But hybrid model like CNN, transformer, and explainable AI offers a better scalability and contextual understanding while integrating the GRAD, CAM, or LINE. But for future work direction, we really need a real-world deployment in the farmer using edge-cutting technology, and also work on the multiple input, not just images, but some soil data or text with image, so that we can work on concrete output and build our model more accurate and knowledgeable. And also need to understand the data set for better generalization and understanding of AI and model, so that we fetch output with the better decision and explain how it works. So
Thank you so much, ma'am, for your insightful and well articulated session. We are open to questions now, if any.
In your class you said that was critical to the model's performance.
Sorry, can you please say again?
Is the question in the chat?
Okay,
His
okay.
question is in chat.
Yes. Okay, so first of all, thank you for the question. It's very interesting. So when I go through with the old transformer and CNN based model, so feature extraction is most difficult because it comes up with multiple layers. But when you go with the explainable AI, it divides your work. So the most critical or not the hardest part, but the complex part is feature extraction part, because you fetch the main disease area from feature extraction and then classify it. So yes, hope it's understandable.
Yes, thank you.
Thank you.
Okay, then if there are any further question, then. Okay, then we will proceed to our next paper. Then I'd like to invite our next paper presenter with the paper title Machine Learning Driven Smart City Architecture, a Scalable Design Approach by Dr. Dinesh Kumar Seni. Sir, it's over to you.
Hello. Am I audible?
Yes, sir, you are audible.
Good morning to the respected session, chair, distinguished professors and panel members and fellow researchers. I am Rajiv Das along with Dr. Dinesh Kumar Sen, and I am delighted to be presenting here today at the 9th TEAS 2025 International Conference hosted in this beautiful country of Poland. Today, my co-author and I will walk you through the research on machine learning driven smart city architecture, a scalable design approach. This work is conducted in collaboration with Dr. Dinesh Kumar Saini from Bhopal University, Jaipur. In this presentation, we aim to share a structured, modular, and a ML design for addressing critical urban challenges that are increasingly becoming global in nature. And first of all, I would like to discuss about the problem statement. Urbanization has transformed how cities function, but not necessarily how they adapt. Modern urban areas are grappling with multifaceted issues such as energy efficiency, traffic congestion, environmental pollution, and security threats. These traditional infrastructure that supports our cities was not built for real-time responsiveness on large-scale intelligent decision making. They are largely static, manually operated, and operate in isolation from one another. Our approach proposes a holistic solution, a scalable modular architecture based on edge computing integration, a real-time decision-making loop powered by supervised and ML supervised solution, a layered model that allows various urban domains such as energy, waste, transportation, and public safety to interact efficiently with minimal latency. We also offer performance validation, showing up to 30% improvement in operational efficiency across these verticals. Our research follows a design science methodology, blending both empirical investigation and technical system development. The methodology involves 5 major phases. The first phase is problem identification and requirement analysis. We conducted a systematic review of smart city challenges across Asia, Europe, and North America. The second point is system design and architectural blueprinting. Based on insights gathered, we proposed a 4-layer modular architecture which emphasizes on low latency, edge computing, ML integration, and interoperability. The third point would be component selection and tool chain finalization. We selected cloud services such as Amazon Web Services, Azure, ML frameworks such as TensorFlow, PyTorch, and container tools such as Docker and Kubernetes, based on scalability, security, and support. Prototype development and simulation. A scaled down smart city environment was emulated using synthetic IoT datasets. Real time simulation tested system performance under variable load from 10,000 to 10 million users. Performance evolution and benchmarking. Matrices such as response time, accuracy, energy usage, and cost per citizen were collected. Our system demonstrates significant improvement over traditional models, up to 30% operational efficiency gains, 89% ML prediction accuracy, and 50% lower deployment cost. Now I would like to discuss about the functional domains of smart city. Before diving into the architecture, let's establish our definition. The 6 key characteristics are energy management, implementation of smart grids with real-time fault detection, transport services, intelligent transport services, which uses real-time traffic routing. AI optimizes public transit schedule based on live demands, waste management, predictive alerts generated from smart bin fill levels. Routes are adjusted dynamically for cost-effective waste collection. The public safety and security, anomaly detection through surveillance video feeds, crime pattern predictions, enables proactive resource deployment. Governance and citizen services, natural language sentiment analysis on citizen feedback, AI-driven personalized portals for public services. These verticals are no longer isolated, they work collaboratively in our architecture. Now I would like to discuss upon the urban infrastructure challenges. Population density is rising, but social disparities remain. The technological hurdles are legacy systems often resist integration, high volume and low latency processing, difficult with older infrastructure. The environmental strain, real-time air quality or water pollution tracking needs new sensor networks. Energy efficiency and sustainability targets are difficult to achieve reactively with the traditional systems. Financial constraints, budgeting for digital infrastructure is often difficult. Government struggles to justify return on investment with visible immediate. Hence, we must design an architecture that is cost conscious, modular and ready for phased integration. Machine learning in smart cities. Now let us discuss about the machine learning categories which can be integrated with the smart city design. Supervised learning, traffic forecasting using random forests or SVMs, crime rate prediction based on historical police logs, energy consumption prediction to enable load balancing. Unsupervised learning, clustering traffic pattern using k-means, identifying anomalies in energy usage and water distribution, user segmentation in smart grids for traffic planning. Now I would like to call Mr. Dr. Dinesh Kumar Saini to discuss about the proposed architecture overview. Over to you, sir.
हाँ करा है टेक्स्ट मैंने ऑडियो भेजी है
Thank you, Rajdeep. Good morning once again to the respected chair and the esteemed attendees. I will now walk you through the technical architecture, use cases, and the measured performance of our system. So, onto the 4-layer architecture design. Yeah. So, we divided it into 4 layers. The IoT sensing layer. We have deployed sensors including, we can deploy sensors including traffic cameras, smart meters, pollution monitors. Communication uses lightweight protocols like the MQTT and the COAP. And the next layer, the data aggregation and storage layer. We have nodes that compress the data, pre-process the data before uploading it to the cloud so that our systems can handle it efficiently. The ML model layer. We deploy inference engines for latency critical tasks. In cloud, we host dynamic forecasting and reinforcement learning agents. ML operations tools such as ML Flow and TensorFlow serving ensure model versioning and deployment pipelines. The visualization and user interaction layer, Grafana dashboards serve planners, citizens engage via mobile apps, developers use secured APIs, OpenAuth 2.0 manages access control. Now let's discuss the key use cases of our application. So our architecture was validated through 5 applied use cases. The first one being intelligent traffic management, real-time optimization of traffic signals. ML predicts the congestion and clears emergency paths. The results were 20%, 24% drop in vehicle wait time. Predictive waste collection, ML predicts bin fill levels, routes are optimized dynamically, which results in significant operational savings. The third being air quality monitoring. Ensemble models predict pollution spikes, alerts are issued for vulnerable populations, industrial operations are scheduled to minimize the exposure. Public safety and crime protection, video feeds are analyzed for anomalies, and predictive policing ensures timely interventions are taken to predict the crime and do the needful before the crime eventually results into a fatal anomaly. Smart energy distribution, real-time demand response optimization, ML detects non-technical losses, load balancing improves the reliability. Each use case proved practical, scalable, and replicable in global context. Now, the technological stack and implementation that we have used are we've built our system using industry tools like the IoT platforms used AWS IoT Core, Google IoT Core, Azure IoT Hub, edge devices like Raspberry Pi, NVIDIA Jetson Nano. Edge processing ensures low latency and high priority tasks. Containers and orchestration, we have used Docker containers and Kubernetes clusters allowing automatic scaling. OpenFaaS enables serverless event-driven computing. And for ML frameworks, we are using TensorFlow, scikit-learn, PyTorch for model building, XGBoost for structured datasets, Apache Spark MLlib for distributed ML. Monitoring, we are then again using Prometheus and Grafana, ensuring the system's health and alerting the individuals. ML Flow tracks experiments and model lifecycle. All choices were made for performance, cost efficiency, and scalability. Now, coming to the security and privacy ethics, smart city is data sensitive, and we prioritize security. So we have provided end-to-end encryption, secure key vaults, federated learning protects raw data, GDPR compliance is strictly followed, ethics fairness ensured through bias mitigation, transparent ML decisions with SHAP and LINE, UNESCO AI ethics guidelines shape our governance. We build trust and transparency into the very foundation. Performance and scalability, let me share some of the benchmarks. Our system supports 10 million users, processes over 1 billion data points a day, 50% reduction in cost per citizen, 99.8% system uptime, 30% automatic failover, data integrity of 99.9%, 4-hour disaster recovery RTO. This architecture meets both current and urban demands. Now I would like to conclude and talk about the impact of this project. We offer a complete ML-enabled smart city architecture. It is scalable, modular, and production ready. It improves operational efficiency across multiple domains. Measurable impacts include 24% less wait time in traffic scenarios, 18% energy savings in energy trading, 5x faster edge response, 89% prediction accuracy. Our vision is clear: cities that are autonomous, transparent, and equitable. Ethical AI at its core, global adaptability for both developed and emerging cities, collaboration with governments, tech companies, and researchers to bring this architecture to life. Thank you, and we welcome for any questions or feedback.
Thank you so much, sir, for your insightful and well-articulated presentation. We are open to questions now, if any. Okay, so if there are no further questions from session chair or fellow presenters, we shall now proceed with our next paper presenter. I would like to invite our next paper presenter with the paper title Mobility Aware Spectrum Handoff in Cognitive Radio Vehicular Centralized and Cognitive Radio Ad Hoc Network with 6G capability with paper ID 460. It's over to you, Nita ma'am. Okay, I guess we proceed further. I would like to invite our next presenter.
Ma'am, am I audible?
Yes, ma'am, you're audible.
Yeah, ma'am, 1 second. I'm just sharing my screen.
Okay, ma'am.
My PPT visible.
Yes, ma'am, it's visible.
Okay, can I start?
Yes, ma'am, please.
So the title of my paper is Mobility Aware Spectrum Handoff in Cognitive Radio Networks with 6G capability. Now, why I have taken this off title? It's because mobility spectrum handoff refers to spectrum handoff strategies in CRN that explicitly consider the mobile patterns, speed, and trajectories of users or vehicles during the handoff session and execution processes. I have taken two CRNs, that is one vehicular centralized network and another is ad hoc networks. So basically, vehicular centralized network is where communication is managed by a centralized entity or infrastructure such as roadside units or central controllers. The key features of centralized network include centralized spectrum management, coordinated handoff and access, and infrastructure-based communication. Example, we can consider a smart highway with RSC deployed every few kilometers. I'll just share the screen one more time because what is happening, I'm not able to change the screen. Can I redo it? Is it visible now?
Yes, ma'am, it's visible. Yes, ma'am, it's visible.
Okay, thank you. And the other network I have included is ad hoc network, which is infrastructure-less network, where CR-enabled nodes communicate directly with each other in ad hoc manner, dynamically sensing and accessing available spectrum. The key features of ad hoc network includes no centralized controller, dynamic topology, spectrum sharing, and routing. For example, a disaster recovery scenario where rescue teams' devices form a ad hoc network. Now, why I have taken study of mobility-aware spectrum handoff in both the networks? The reason is, number one, there is a need for mobility-aware spectrum handoff due to high mobility challenges, dynamic spectrum environment, and 6G requirements. And why I have taken two networks? Because in one of the network, that is centralized vehicular CRN network, there is centralized management optimization, reduced handoff frequency, efficient resource utilization, and enhanced quality of service and reliability. Why I have taken cognitive radio ad hoc network? Because it has distributed decision challenges based on mobility patterns. It maintains connectivity in highly dynamic topologies and leverages 6G capabilities also. So this ensures reliable, efficient, and seamless communication in the next generation intelligent transport and ad hoc systems, addressing mobility-induced challenges that existing protocols cannot handle effectively. So the proposed integrated handoff model includes dual spectrum pools, that is licensed and unlicensed pools. Before starting this dual spectrum pools, I would like to tell you something about licensed spectrum pools. So licensed spectrum pools consist of frequency bands that are allocated to specific primary user by regulatory authorities. It contains primary users which hold exclusive rights to use these frequencies, and contains secondary users that can opportunistically access these bands only when TUs are not using them. And another spectrum pool is unlicensed spectrum pool that includes frequency bands that are open for public use without the need for individual licenses. Example 5 gigahertz band, 60 gigahertz band, which are used for Wi-Fi and Wi-Fi. So I have taken, as I have told, that I have taken different handoff strategies. So before starting with different handoff strategies, I would like to tell something about intra-pool and intra-cell, intercell and interpool handoff. So there are two different terminologies. One is intra-cell and one is intercell spectrum handoff. Intra-cell handoff occurs within the same cell and connected to the same base station to a different channel. Inter-cell spectrum handoff involves moving to a different cell. The user switches both the channel and the base station. Then we have two different topologies called intrapool and interpool. Intrapool is particular handoff where secondary user switches between channels within the same spectrum pool. And in interpool spectrum handoff, secondary user switches from a channel in one spectrum pool to a channel in another spectrum pool. So I have taken in my study the four different handoff strategies where I have where I have done Monte Carlo simulations for all the four handoffs mentioned here. So I have taken few parameters before analyzing the study. One is blocking probability. Like in most wireless communication, what happens? This is very mandatory to calculate blocking probability to compute quality of service of a system, which is the probability that a secondary user is unable to access any channel when it needs to transmit data due to unavailability of free spectrum and resources at that time. So I have also taken the switching time when one of the particular user, secondary user, switches one from one channel to the other channel. And another parameter which I have taken is wait threshold, or it is also called the delay threshold, which is designated as DTH, where it refers to the maximum allowable time duration within which a spectrum handoff must be completed to ensure that quality of service is maintained and ongoing communication sessions are not disrupted. So in my analysis part, what I have calculated link maintenance probability and link failure probability. Link maintenance probability measures the likelihood of a secondary user that it successfully maintain its session during the spectrum handoff, and the opposite is for link failure probability. So for my analytical and simulation validation, I have taken Monte Carlo simulations, which is a statistical technique that uses random sampling and repeated simulations to analyze, estimate the performance of a complex system that have uncertain, random, or probabilistic behavior. And I have also taken different performance evaluation parameters like blocking probability, spectrum utilization efficiency, handoff success rate, throughput, and delay. Because what happens in Monte Carlo simulation, it does the same. It also does the protocol validation. It also optimizes the network. So while this I have already explained case study 1 and 2, what is the difference between the vehicular network and the ad hoc network. So after analyzing all the comparative four secondary user handoff schemes, it came to a conclusion that vehicular centralized network is more effective as compared to ad hoc network because it has higher link probability, and it has lower link failure probability. So after the conclusion, after I studied all the parameters and done the simulations, it came to conclusion that For a robust CRN network, the dynamic vehicular environments,
Actually, I'm busy. Who are you?
cognitive vehicular centralized ad hoc CRN network is preferred as compared
Yeah,
to
I'm busy right now.
ad hoc network. So this is the end of the slide. So in
Ma'am,
case
एक
of any
second.
queries, most welcome.
Thank you so much, ma'am, for your this interested and well articulated presentation. We are open to questions now, if any. Okay, so if there are no further questions from our session chair or audience, we shall now proceed to our next paper, with the paper title "Enhanced Predictive Analysis of Brain Tumor Survival Using Multimodal Data Integration." Paper ID 338. I would request Miss Aditi ma'am to please take over.
Am I audible?
Yes, ma'am, you're audible. Ma'am, it is requested to
Okay.
please stay within time limits as we have a limited time.
Yeah, sure.
Okay, ma'am.
Sure. So, a very good afternoon to one and all. The presentation is titled Enhanced Predictive Analysis of Brain Tumor Survival Using Multimodal Data Integration. This presentation will cover the introduction, literature review, methodology, model, architecture, key results, discussion, and conclusion. Brain tumors, especially glioblastomas, are highly aggressive with poor survival rates. Early and precise detection is critical. Yet traditional manual MRI analysis is slow and error-prone. So the recent advances in the deep learning and machine learning enable the automated tumor detection and survival prediction by combining the radiomics features with clinical data to support personalized treatment planning. Advanced CNN models such as tumor.net, YOLO V7, and BCM CNN have demonstrated excellent accuracy in brain tumor detection. Techniques including transfer learning, attention mechanisms, and lightweight deep learning models improve speed and efficiency, enabling real-time clinical applications. Furthermore, combining radiomix features with clinical and genomic data enhances the survival prediction accuracy. And innovations like data fragmentation, federated learning for privacy, and explainable AI methods improve model generalizability and interpretability.
Okay, ma'am.
Here's the methodology. The dataset included approx 10,000 MRI images from TCGA and Kaggle, representing pituitary tumors, meningiomas, gliomas, and non-tumor cases. Clinical information such as age, gender, tumor grade, and treatment history was collected. Radiomix features like covering intensity, shape, and texture were extracted using biradiomics.
Sorry, your slides are not advancing.
Hello?
Ma'am, your slides are not advancing.
And now, is the model architecture slide is visible?
Yes, ma'am.
Okay. So this is the model architecture in which we are giving the MRI scan images to the model. Then pre-processing technique is applied to remove noise and all. And then segmentation of the MRI images is done. The next is the tumor classification. Then the clinical data integration is done. And then finally the features are selected which are used for the survival prediction of the brain tumor patient. The pipeline begins with MRI pre-processing through techniques such as contrast normalization and stripping, followed by tumor segmentation using advanced models like UNIT. Ready-made features are extracted from the segmented regions and integrated with clinical data. CNN-based classifiers with CBAM, attention, and SPPF plus layers improve the tumor detection accuracy. Feature selection refines survival prediction inputs, which are processed by machine learning models, including SVM, random forest, and XGBoost, to predict patient survival time, supporting the personalized treatment strategies. These are the results and findings. Here we have used the accuracy and DICE scores for the tumor detection, and for survival prediction, C-index and RMSE is used. Performance of tumor detection. Across all the tumor types, the suggested CNN plus CBAM, which is the proposed model, obtained a DICE score of 0.92 and an accuracy of 99.5. In comparison with the existing techniques like ResNet 50, which has obtained a DICE score of 0.87 and 96.5% accuracy, and YOLO V7 had a marginally higher accuracy of 99, but it was not as replicable. This table presents the detailed evaluation metrics for tumor detection, highlighting the robustness of the proposed model. This is the graphical representation of the above table. Now the performance of survival prediction. In survival prediction, the SVM-based model 0.85 with an RMSE of 3.2 months, while random forest achieved 0.78 and logistic regression 0.72. This is the survival tumor detection by concentrating on pertinent areas of MRS accuracy. And for survival prediction, when combined with the clinical data, RadioMix features improve the predictive reliability by offering important insights into tumor biology. The proposed method achieves a state-of-the-art performance in both detection accuracy and survival prediction reliability, offering significant potential for personalized cancer treatment. Future research will investigate the multimodal data fusion, integrating genetic information with imaging data to further enhance the predictive performance. Here I conclude my presentation. Thank you.
Thank you so much, ma'am, for the insightful and well-articulated presentation. We are open to questions now, if any. Okay, so we proceed for further with our next paper presentation with the paper title The J-Curve of Productivity, Measuring the True Impact of Digital Business Assets and Financial Technologies on Economic Growth with paper ID 52. I request Alisa ma'am, please take over.
Hello to everybody, and do you see interaction demonstration of PowerPoint? Do you see the presentation to everybody? Distinguished colleagues and professors and fellow researchers, in the former we present today the core findings and conceptual advantages of our present research, considered in collaboration with Dr. Marzena Sobchak-Michalovska and Dr. Svetlana Kashova. Our paper is titled The J-Curve of Productivity, Measuring the True Impact of Digital Business Assets and Financial Technologies on Economic Growth. Okay. The part of our study is enduring products activity by Robert Solow, who says you can see the computer age everywhere, but the productivity, but in the productivity statistics. This observation, despite decades of digital advances, continues to challenge the empirical understanding of how transformative technologies translate into measurable economic growth. While information and communication technologies, artificial intelligence and fintech have reshaped economic structures, the impact remains inconsistently captured in national accounts. We argue that this is due a significant under-recognition and integral capital, especially digital business assets and financial technologies. Okay. Our central hypothesis is that productivity metrics suffer from temporal misalignment between when investments in digital infrastructure are made and when their benefits materialize. This leads to a drop-off pattern. In the early phase, measured productivity stagnates or declines due to unmeasured immediate investments. In the later phase, productivity appears to struggle, and as accounted capital sales starts contributing to output. This G-shaped trajectory mirrors patterns observed historically when general-purpose technologies like electrification, steam engines, and now digitalization in economies. A theoretical model and methodology. To formalize this intuition, we expand the classical solo growth model to include a vector digital asset, DA, that emulates the official accounts, an argument production function incorporating shadow pages of inevitable investments derived from Tobin's Q theory, the computation of total factor productivity, TFP, J, approximation from understanding inputs and underestimation from an instrument output. And next. So we have such equations to our theoretical model and methodology. And we have such empirical evidence and results. Using a multi-decade panel from 1961 to 2024 and market valuation techniques, we estimate the following. First, software and fintech risk assets show the strongest J-curve effect within 15.9% productivity underestimation in 2024. Hardware investment through jungle showed reliability, weaker investigate components, and smaller disadvantages. The productivity contribution of AI-raised in integral capital are growing through still modest. We constructed adjusted productivity theory demonstrating that traditional TFP measures underestimate true growth by 11.3 till 15.9% in recent years. Then policy and account implications. Our findings turn to current statistical approaches in national account. But finally, to treat digital platforms, fintech ecosystems, and data assets as capital, official GDP figures systematically mislocate investment contributions. This has three major implications. First, macroeconomic policy may understandable the productivity payouts of digital transformation program. Second, central bank and regulations may measure output gaps and inflation pressures. And third one, investment incentives for intangible insensitive sectors may be measured by underfunded. Okay. Conclusions and future research. Our result, the estimated level of impact digital business and asset financial technology on GDP is shown on the table. And the conclusions and future research, we conclude that the short J-curve of productivity is a structure at the heart of digital capitalism. The model explains not just the delay in productivity payouts, but also the automatic relation of digital assets across sector time. Research will be disaggregating the model by sector and firm size, including differentiation parameters in short, limited sizes, and explore machine learning approaches to estimate real-time activity corrections fact. Thank you for your attention and welcome your questions and critical engagement.
Thank you so much, ma'am, for your insightful and well-articulated presentation. We are open to questions now, if any. Okay, so then we will proceed with our next paper presentation with the paper title Deep Learning Based Feature Identification for Ocular Design Detection using VGC16 model with paper ID 321. I would request Gurpreet ma'am to please take over. Ma'am, I request you to please stay within time limit as we have a very limited time.
Yeah, sure. Am I audible to everyone? My screen is visible.
Yes, ma'am.
Okay, fine. Good afternoon, everyone, esteemed colleagues and honored guests. I recruit for research scholar from MMU Maulana Ambala, India, and I'm delighted to present my paper, which is based on the topic Deep Learning-Based Feature Identification for Ocular Disease Detection using VGG16 model. I'm excited to share my insights with you, and I'm look forward to your feedback and discussions as well. Ocular disease is any kind of form or a condition that can affect the power of eye and operate appropriately or harms the eyesight. Much of the world's ocular pathology has a complex disease ratio. According to the several related preparations, around 400 million persons will be affected by the DR by 2030. These types of disease are becoming a central worldwide health alarm. CNN models among them are one of the most beneficial for interpreting and processing medical pictures in fundus and retinal imaging for ocular disease categorization. Existing CNN-based model normally require a huge data set to train, and because illumination, resolution, and imaging methods vary, their performance may deteriorate when exposed to images from different sources. This research contributes to the field of ocular disease recognition by carefully examining DL-based feature extraction techniques. This work uses transfer learning and VGG16 model to enhance the detection of significant visual patterns in ocular images. The next one is objective. The main study mainly focused on the feature extraction using VGG16 to maximize identification of critical ocular disease feature, improve classification accuracy, and reduce computational complexity. Then we'll discuss the various problem statements. Mainly the accurate and the efficient detection of ocular disease remains one of the major challenges in the medical image analysis. While various kind of models, if I discuss like CNN or DLL, have demonstrated in OD classification, feature extraction is one of the most common problem for them. So another challenge which I have faced while doing work with this, that in the variation in the imaging parameters, for example, there is such differences in their contrasts, in the resolution, in the lighting, in the various kinds of data sets. Without effective extraction of the most relevant and high-level features, model decrease the classification accuracy, increase the computational complexity, and ultimately limiting their practical applications in the real-world ocular disease diagnosis. This is my proposed flow chart. In this flow chart, firstly, I will take the images from the database. I have used ODIR, that is Ocular Disease Intelligent Recognition data set, from where I have taken various kind of images, and then I will resize the image into certain patterns, like by 240 by 240. I've resized the image. Then we'll apply various data augmentation techniques over these images by using various conversion techniques like RGB to gray. And if any kind of noise identified, we will add periodic noise to this until or unless we will not get the optimized image. And if no noise found in the image, then we will apply the filtration process in this. We used Butterworth band pass filter in this. Then our data will send for the feature extraction process. We will use pre-trained VGG16 model for this. After applying this method, we will extract the features from the various kinds of images on the basis of 8 categories. And then we will store the feature set extracted from the model into the database for the further process, that is feature selection process. Let me highlight. These are the proposed work phases. The first phase is data gathering. I have taken the images of 500 patients from ODIR data set. This data set captured the images from the various kind of cameras on the basis of different resolutions. So the label represents the different ocular conditions. Basically, it is divided into the different 8 categories. That is, N denotes here normal, D for DR, G stands for glaucoma, C for cataract, A for age macular degeneration, and H stands for hypertensive retinopathy, M is myopia, and O is optic neuropathy. It is divided into various 8 categories. After the data gathering process, we will apply the pre-processing technique. In pre-processing technique, we will rotate the image into the different angles, 90 degree, minus 90 degree, plus 180 degree, so that the rotations keep the model from being skewed by the ocular image orientation. After applying the pre-processing techniques, then we'll convert the image into the grayscale conversion. This grayscale conversion computation reduces the number of color channels while retaining essential structural details, as it is shown in the figure as well. After that, we'll apply the filtration method. I have applied the Butterworth pass filter to remove the unwanted features and any background image to improve the image clarity. Then I iteratively will repeat this method again and again to clean for the clean and high quality images, so that we can proceed to the next stage by reducing the risk of misleading patterns affecting model performance. After completion of the noise reduction, the images were considered fully pre-processed for feature extraction. This is the highlight of feature extraction model of VGG16. It is well-established CNN model which is used as a feature extractor. It's a deep learning hierarchical structure having 7 low-level to high-level features. It takes the image of 224 into 224 into 3 channels, having various max pooling and convolutional fully connected and softmax layers in this. Various results in discussions show that VGG16 model got better result as compared to the other model. For example, LXNet. This shows the comparison. This shows the comparison between the VGG16 and LX model. While comparing these two models, after various calculations, after applying various techniques like mean and standard deviation methods, these feature extraction particularly calculate the mean and standard deviation methods. For the machine learning and data analysis, the mean provides the average value, where the standard deviation indicates the spread or dispersion of data around that average. This graph shows that the mean average and the standard deviation for the feature extraction of the model VGG16, how it works. This is the graph which shows the difference between VGG16 and LXNet model. After comparing the two models, the conclusion is that the VGG16 completed its feature extraction in 49.69 seconds, whereas LXNet required 55.23 seconds for the same task. This indicates that VGG16 is approximately 5.5 seconds faster, making it more efficient choice for the feature extraction process. So this result suggests that VGG16 creates a better balance between the speed and the performance, as both models are well established for extracting deep features. The last slide is all about the conclusion. According to the present study, the LXNet and VGG16 methods for feature extraction and ocular disease both are effective, but the performance on this classification task was significantly improved by the retrieved features. So while selecting the best model for the medical image analysis, the comparison reveals that trade-offs between the various designs regarding processing time and efficiency. Future research can investigate how to further enhance retrieved features further using sophisticated optimization algorithm for the feature selections. So that's all. Thanks everyone. Any questions? Thanks for listening. You can ask any questions from me.
Thank you, ma'am, for your insightful and well-articulated presentation. We are open to questions now, if any. Okay, so then we proceed further. With that, we conclude today's paper presentation session at NICE TEAS. We sincerely thanks to all our presenters for their valuable contribution and to our audience for their active participation. A special thanks to our session chair for guiding the discussion with clarity and depth. I would now request all of you to please switch on their cameras so that we can take a virtual photograph to capture this memorable event.
I'm sorry, my presentation. Innovation method for context identification of a fragment.
Sir, actually I called you at a very first place. Could you please come in the next session as we have a next session scheduled at 4:30?
Okay.
At 4 o'clock, sorry. I'll share the meeting link in the chat box. Thank you to all. We look forward. Thank you to all. We look forward to seeing you in the next session. Have a great day ahead. Thank you so much, ma'am, and thank you so much, sir.
Thank you everyone.
Thank you.